Now, the other side of that I just wanted to see the happiness first before I just ripped it out of there. We won't have homework tonight so long as people are on task and like following along with the lecture and stuff. Because it's easy to like throw it in mid-lesson.
My homework period it was page 119. Because that's the one that game's just true.
Yes, if you're done with it, you are going to have no homework on a night when everybody else does. Cool. Awesome. So, chapter 5, remember, you guys should have all this already, but we're looking at thermal energy. That's the entire focus of chapter 5. And the reason that I tied this together with chapter 4 is because energy is energy. It's just how it manifests or presents itself. Whether it's kinetic or gravitational depends on movement. But it turns out stuff that doesn't move can also have energy in it, and it's called this. So, again, you should already have this first definition. We define for ourselves the idea of temperature. And I'm going to shorthand it with temp. In our country, we measure typically with what? Fahrenheit, degrees Fahrenheit, and nowhere else in the world I don't think will you find that as the norm. Everywhere else uses what? Celsius, or the metric system. And if you want to be real specific with it, Celsius isn't really truly the SI unit either. Kelvin is the SI unit. For our purposes, I'll specify if we have to have it in Kelvin, but most of the stuff that we wind up doing, it winds up degrees Celsius that we deal with. Celsius is much nicer than Fahrenheit. 0 Celsius is an important number because what happens at 0 degrees Celsius? Water freezes. What's the other important number?
200.
So that's Fahrenheit, and it's awful and arbitrary seemingly. 100 Celsius is where water does what?
Freeze.
Boils. Cool. Not freeze, boils. Okay. Now, as we're looking at it, we define temperature, though, as well as, and I'm going to rewrite it just in case you missed it. Temperature, by definition, is the average something.
Oh, the average kinetic of particles.
The average kinetic energy of particles. That is what the temperature actually is.
The makeup matter.
Yep. Of particles. Yo. Okay. Make up. Yes, sir. Yeah, hostile. Matter. Cool. Now, beyond this, we didn't write anything else, right?
Yes, we did.
What?
Temperature scales, and we wrote degrees Fahrenheit. We wrote like.
Wait, we wrote that.
Yeah, we did write that.
Yeah, that's what he's saying. Did you not?
No.
Okay. So if you didn't, we'll just jump in right here. And it might look a little bit different here, Sonny, but I can't help it. I didn't write it down. Cool. We have Fahrenheit, which is awful to spell, here. We run from 32 degrees Fahrenheit to 212 degrees Fahrenheit. Okay, that's water freezes and water boils. And I know we talked about it, but if you didn't write it down, now's your chance. We also get this idea of Celsius, which this is from water's point of view. 0 hot in water is when it freezes, and completely hot water is when it starts to boil. This number scale is so much nicer. Beyond that, just so we have it, and I never remember the number off the top of my head. I think I do, but we could fact check it. Kelvin is the real SI unit. Now, what's ugly about it, one, is that water boiling and freezing temperature is weird when you look at Kelvin, but we're going to say negative 273.15 degrees Celsius is exactly equal to 0 Kelvin. And I'm going to write just a capital K. There's no degree symbol here. 0 K is Kelvin. Now, this has a name. This is absolute zero. This temperature cannot truly be reached. We can get really, 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 really close to absolute zero, but we can't get to absolute zero. If you were to get to absolute zero, the energy just stops being energy, and time would have to stop as well. A bunch of crazy stuff happens. No matter how much energy we try pumping into something to get it to cool down via fancy fridges and things like that, we just cannot make it happen. We can get really close, can't get there.
What about dry ice?
Dry ice runs at like negative 95 or negative 195 Celsius.
So,
You can get way colder than dry ice.
what would happen at absolute zero time would stop?
It would have to, but time can't stop there if it doesn't stop everywhere.
Yeah.
Yeah, there's weird stuff that happens. Yep.
Say would it
Wait.
only stop in like the freezer that you made at
So The good news is that it won't because we can't reach it. No matter how hard we try, we get really close. Just like the speed of light. We can get to 99.9999999% the speed of light, but we can't actually get to the speed of light because stuff gets weird and physics breaks down. There's not enough energy to make that happen in either direction. Okay, now the last little change here. A change in, let's see, 1 degree Celsius change is equal to 1 Kelvin change. Which means it doesn't matter if you're looking at Kelvin or Celsius. If we have some change in temperature, it's going to be the same change in Kelvin as it is in degrees Celsius. So water exists over what degrees Celsius again? What temperature Celsius does water exist? Liquid water. Sure. From 0 to where?
Oh, 0 to 100.
So that means there's 100 degrees where water's liquid. Are you guys cool with that? There's also 100 Kelvin then where water is liquid. Just instead of it being 0 and 100, it looks like it would have to be negative or 0 Kelvin to, goodness gracious, 373.15.
What would absolute zero be in Fahrenheit?
Don't know. Not a clue. 400-ish. Really cold. Okay. We will work primarily with Kelvin. Sorry, it's Celsius. All right. That's what we talked about last class, and hopefully we're all up to speed again. Beyond temperature, the next big idea that we're looking at is thermal energy. So all of these things are related, and we'll see the relationship later in the class, just so you know, but they're all just slightly different variations of thinking about and how we interact with energy in this form. So we're going to define for ourselves thermal energy. Okay. Temperature is the average kinetic energy. We want to make sure that we keep that. The average kinetic energy is how we define temperature. And it winds up being in joules then, and we do these fancy changes to make it into something that makes more sense to us. Celsius degrees or Fahrenheit degrees. Thermal energy is a little bit different. Instead of being the average of the kinetic energy, we're going to say that thermal energy by definition is the sum of all kinetic and potential energy, kinetic and potential energy, of the particles in an object. And here's, before I write in an object, there's a weird little thing that I'm being hesitant with. If I think of a cup of coffee and it has a bunch of liquid in it, can we all agree that the liquid inside that cup is the object? It's weird to think about the liquid as being an object, but we have to play with the language in another way. In a material or an material? So there's, I already wrote an is why I would sing it like that. Should we say in a material instead of an object? Is liquid any more of a material than it is an object to you? Okay, I'm fine with keeping it as an object. Okay. Now, looking at this, first little thought that I want us to just see if we can't put together. Quick question, and I don't know if we talked about the alliteration in here, but I like it when things alliterate. If it's brown, put the pencil down. So this is just to talk about. Check it out, it's brown now. Cool. All right. Yeah, just a stupid little rhyme. I want you guys to think about this. Which is greater? I want you to make an inequality sign, so one of them should be bigger. And we're just saying we're talking about the same cup of coffee, okay? I want to know, is the thermal energy in that cup of coffee greater, less than, or equal? You're just going to put that symbol right here, and you can just say it with words, to the temperature. Cup of coffee, doesn't matter, any liquid you want, as long as you're talking about the same cup of liquid. Does it have more thermal energy, or does it have more temperature? Talk it out. It's a weird question. See if you can navigate through it. I'll give us a minute or so. We're going to make this an example, and we're actually going to include it. So here we go. Let's see if I want to see anything else about this. Cool. Let's think about this. Let's compare. So we'll just do a quick example, and it's kind of like a thought experiment, but we're going to make it a little bit more concrete. Consider an object or a cup. We'll say an object. I'm fine with that. How many particles of whatever's in this are we dealing with? Give me a nice number.
30.
Okay, I'm gonna go smaller. I shouldn't have even asked. Can we imagine there's 10? Why would I ask? Why would I ask? Okay, an object has 10 particles.
Is that true though? Or no?
No, they'd have maybe 10 billion or trillion. Like even, unless it's tiny, yeah, it depends. Okay, so check it out. I'm gonna draw my object, and it's just gonna be a square. Roughly a square, rectangular type shape. Here's the object that we're looking at. Okay, and I need how many particles? 10? Cool, so check it out. I'm gonna make 10 particles. You should do the same. 2, 3, 4, 5, 6, 7, 8, 9, and 10. Here's an object. It's two-dimensional. It has 10 particles. With 10 particles, are they moving? They should be, right? Because that's, unless it's absolute zero, they have to be moving at least a little bit, and they can't be absolute zero. So check it out. Pretend right now that these had convenient values of energy. Now, real particles will have nowhere near this much. Can we say each has 1 joule? So let's say each has 1 joule of kinetic energy. Each has kinetic energy equal to 1 joule. And then just for argument's sake, we're also going to say they all have potential energy because there's interactions that occur at the small level. So we'll say they have kinetic energy of 1 joule and potential energy of 1 joule. So they're right in the middle of where they want to be. All the way from being way as hot as it could possibly be to as cold as it could possibly be. They have kinetic and potential energy. Okay, everybody else still on board? Let's check this out. From this experiment or this thought process, I want us to do 2 things. On A, calculate the average, and I'm going to use AVG for average, kinetic energy. How do you find an average?
You add them together. And
Okay.
you find, like, 2.
So you take all the kinetic energies, add it up. Careful, I don't like to divide by 2.
Don't we
Dividing by 2 only works if we're finding the average between 2 things.
divide by
Are you
how
okay?
many numbers are to like add?
Okay, so if we write this out, and I'm going to write it, it's the sum of the kinetic energy divided by the number of particles. Are you guys okay with that?
Yes.
Okay, what do all 10 of these particles add up to?
1.
So each of them is 1, and there's 10 of them. So we have 10 joules of kinetic energy that adds up. Everybody still on board? Divided by 10, what's the average kinetic energy? This is the average kinetic energy in here. To find an average, you would have to. Is everybody still on board with this?
Wait, where'd you get 10?
Because how many things did we add up?
10.
Klein, go get me a drink. Okay,
You really need 1 too.
cool. You should get yourself a drink, really. On B, I want you guys to do the other thing for me. I want you, instead of calculating out the average kinetic energy, which I could have called what instead? What's the average kinetic energy called? That's the unit. It's the temperature. We just found that the temperature, and it's weird to think about, but we could say that the temperature, is 1 joule. It's strange, but we could. I want you guys at your desks then to do me one more thing. I want you to calculate out for me the thermal energy. Okay, in this object. Chat it out. I'm going to give you a second. I'll come around and help groups, like individual groups as needed. You guys can handle this math. I guarantee it 100%. You all can do this. Every single person in here, even if you think you're bad at math, you can do this. All right. We didn't talk about where this potential energy comes from. Cool. Yeah, why did you not come back with everybody else? No, not you.
I was working on my test.
Where were you working? Where everybody else was? How come you didn't come back with everybody else?
No, I don't think anyone dropped it.
Who
Guys,
did-
you forgot Leo.
Weird. Okay. Strange. Hopefully you got some stuff done. You're a little bit behind at this point. This is why I need reminders, just for the record. Like, I wasn't kidding when I made the comment. Yeah, I missed it too. I got used to you not being here. Sorry, because you were gone for like 2 weeks.
1 week.
1 week. My days just run together. Anyway, check this out. How many particles are there still in here? And each particle, and we're going to make some little comments here. Each particle has what sorts of energy?
Kinetic and potential.
Okay, so it has 1 joule of kinetic plus how much potential? Which means every single particle has how many joules of thermal energy? So careful. Every single particle has 2, right?
Oh, yeah.
How many particles are there?
Okay.
With 10 particles, we get the thermal energy to be what? Okay. Now, where this, no, why, what are you multiplying? 10 times 2? Okay. Thermal energy is 20 joules. Now, where this winds up absolutely bonkers. First off, does this thing have more thermal energy or does it have more temperature? How many joules of thermal energy does it have?
It's 1.
2.
Temperature.
Okay, no, don't change your question. How many thermal energy joules does it have? How many joules of energy that's been averaged and called temperature does this one have? Which one's bigger? So which one, does it have more thermal energy or more temperature? Okay, the weird part about this. I can imagine a situation where I have a liquid, and we can talk about whatever liquid you want. I have a small amount of it that's really, 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 really hot, and a large amount of it that's really chilled. I can have a small cup of coffee have more thermal energy than like a bucket of water. The temperature and the number of particles winds up mattering huge in these calculations. All right, because we always have to add up to all the kinetics, all the potentials, you will always find thermal energy is going to be greater than the temperature.
Always?
Always. Now, it's weird because anytime I say temperature, you guys want to think degrees, but that's just the way that we interpret the joules that they have. Okay, moving forward, tomorrow we are going to discuss heat, which seems like the same thing as these first two, but it's not. Cool. Thermal energy, temperature, and heat are 3 related ideas, but they are different. All right. Catch you cool cats and kittens tomorrow. There is no homework. Thank you. You should finish these. It'll be a better grade if you just bring it to me tomorrow. Okay.